Um, Thank you, Jay, for inviting me. Thank you, Elephant, for the fabulous indie pop. Thank you, Hiroshi, who's probably downstairs somewhere now, for the really cogent description of what gravity is. And my goal tonight is to give you a good warm-up for DJ Mulat. And this is, I'm going to talk about black holes, which are without doubt the weirdest things in the universe, and really, really fun to think about and try to understand. And we think that in doing so, we're going to learn some really interesting new things. Now, in the last several decades, black holes have come to center stage in many different areas of modern science. Of course, they have become even more interesting in theoretical physics, where they started, but now we're seeing them in the sky. They have amazing properties. As I'll explain, they're probably the best computers that can exist, even in principle. And even more important, as you've all learned tonight, they've become into the center of the science of mixology. And here we even have a proof of Hawking's thesis that black holes evaporate. You can see it right here. Okay. So what am I going to do? It's a huge subject. I can't cover it all. But I'm going to talk about the very basics. I'm going to give some history, and then go talk about why they're so incredibly confusing, and then go on and talk about what we're doing right now, because it's a very active subject right now in different areas of science. So what is a black hole? Well, if you're on the Earth, you have to jump pretty hard. You have to get started at 11 kilometers a second to escape the Earth's atmosphere and be free out in outer space. On the Moon, you don't have to jump as hard, just 7 kilometers per second, and then you can escape the Moon's gravitational force and go out into space from the Moon. But imagine if you had an object which was so big that it made such a gravitational force that nothing could get out unless it was going at the speed of light. And then you remember, Einstein told us nothing can go faster than the speed of light, so such a thing would have to be a dark object, hence the name black hole. Now, Einstein's theory, which Hiroshi told you about, was after his 10 years. In 1915, he wrote down some really, really beautiful equations, thought they would never be solved. And a year later, Schwarzschild solved them, and the solution, he solved them exactly, and the solution that he came up with is now known as a black hole. But it has, even from the beginning, it created a lot of confusion, and we're still confused. We've basically been in a more or less constant state of confusion for over a century. And Einstein himself, even though the solution is completely explicit, most people believed it wasn't real. It's really hard to understand now why they thought it wasn't real, but it's definitely so. And Einstein wrote a paper in 1939, 25 years after Schwarzschild found his solution, explaining what was wrong with it and why black holes didn't really exist, and saying things and publishing them in a paper that I or anyone who teaches general relativity would flunk him for saying. And it's not that Einstein wasn't a smart guy. He was a smart guy. It's just that black holes are really, really confusing. Now, there was a lot of thought that went into it. And after 60 years, some late 60s, 70s, people finally started to understand what a black hole was. And Hirose gave some nice explanations of the properties that they have. And now we know, just really in the last few decades, and more precisely in the last few years, we know not only do they exist, but they're just plastered all over there up in the sky, and we're trying to catalog how many there are, and we're looking at their signals many people are using different methods trying to infer their existence. So not only the weirdest things in the universe, they're kind of all up there looking down on us saying, figure me out. So that is indeed what we are trying to do. Now, classically, as you saw from Hirose's picture, a black hole is nothing. You saw that picture, it was just a dark spot. It's like a hole in the end of space. And when I say nothing, I don't mean like there's nothing right here. There's air here. But we could pull the air out and then we'd have a vacuum. I don't mean there's a vacuum, because a vacuum is still something that exists in space. There's a sense in which there isn't even space inside a black hole. They're the most profoundly simple objects that exist, and before we understood them mathematically, we probably couldn't even have thought of something so simple. They're unlike stars. Every star is different. Every star has a different number of atoms and different compositions, and the atoms are moving around in different ways, but black holes are what we like to say universal. They're all the same. And the famous John Wheeler, who invented the word black hole, said that, described that by saying black holes have no hair. They're featureless, simple objects. Now, just when we thought we understood them, along comes Stephen Hawking in 1974, and he said, well, all this discussion of black holes, it's in classical physics, and we know that the real world is quantum and things are subject to an uncertainty principle. Everything must be subject to the uncertainty principle. Nothing can escape it. And one of the things that can't escape the uncertainty principle is the edge of the black hole. It's moving around. So when Hirose was trying to send his emails to Kyoko and she didn't hear anymore, it could have happened that, the horizon fluctuated in and one of them managed to pop out, and in the same way, radiation comes out of a black hole. And Hawking wrote a very famous formula for the temperature of the radiation as a function of all the constants of nature and the energy or mass of the black hole. In fact, it's such an important formula that Hawking had it inscribed on his headstone, which is between Newton and Darwin in Westminster Abbey. I should be using this, shouldn't I? Boo. Maybe I shouldn't be using this. Yeah, right there. The temperature is a function of the mass. Now, there's another famous equation. Very few scientists have equations which are so important that they go on their headstones, but here we've got two of them, Hawking and Boltzmann. Hawking was one of the great scientists of the 20th century, Boltzmann one of the great scientists of the 19th century. And his equation relates information theory to thermodynamics and statistics. And you can combine these two equations into a really fundamental and shocking formula, which is the formula. So everybody's used to the idea of the number of gigabytes in your phone. Well, Hawking and Boltzmann gave us a formula for the number of gigabytes in a black hole as a function. Where's the red dot? Oh, there it is. As a function of its area, Planck's quantum constant, Newton's gravitational constant, and Boltzmann's information constant. So this is how many kilobytes there are in a black hole. Now, it's a very strange formula. Usually you have a formula like the Einstein equation belongs to general relativity. The Schrodinger equation belongs to quantum mechanics. Newton's equation belongs to gravity, so on and so forth. This formula uses every constant from every one of the main areas of physics, so it's kind of a unifying formula for all of physics. And it's a very powerful formula, and as you'll see as the talk goes on, we don't really understand why it's true. But we think that by trying to unravel this formula, we'll understand a kind of unity of different parts of nature that this is the key into understanding how all the different aspects of nature are related. Now, it's a big number. You could fit all the information in the Google data banks into a black hole, which is a trillionth of a millimeter, far smaller than an electron. And in fact, this is trouble for Moore's law. That is thought to be, a black hole is thought to saturate an information bound, in that it's not possible in principle. Of course, it's not possible in practice, but never possible, even in principle, to put more information in a region of space-time than in a black hole. So just your phones stay the same size, and according to Moore's law, every 5 years they double in information storage content. And if you keep this up for 300 years, which is a very long time, all of our phones will have to be black holes. Okay, now if you were listening carefully, I told you two things which were the complete opposites of one another. One is that a black hole is nothing, and the other is that it's the best computer you could have, the best information storage device you could have, even in principle. How are these different descriptions of black holes, how are they compatible? In other words, where do you, if you open your smartphone, there's like a place for the chips, but there isn't even space inside of a black hole. How could this possibly make any sense? Well, this was a huge puzzle for many decades. So first people didn't understand whether black holes existed or not. Finally, that was settled after 60 years. And by the way, I want you to take notice of the timescales for problems in physics. It's not next year. We don't have a 5-year plan. We work on decades. This one has been going for a century. And now, then enters string theory. So as Hiroshi discussed, string theory is a candidate for a theory which is consistent with both quantum mechanics and gravity, and so it can hold this story. There are string theory and there are quantum mechanics, and they're both in gravity. And if string theory is right, and we can control it enough to do the calculation, it better give exactly the right answer. It better reproduce that weird formula that I showed you several slides ago. And in fact, we showed that it did. And the way it does it was very instructive. There's a kind of hologram on the boundary. So if you've ever seen a hologram, you have a two-dimensional image, and you shine a light through it, and it projects a three-dimensional image. And but the boundary, the holographic plate on the boundary is very complicated and stores all the information. And that's possible because its size is proportional to the area, the information is proportional to the area of the black hole. And this all worked out very beautifully, and we found that the maximally simple objects and mathematically maximally complex objects were equivalent, and this was perfectly consistent mathematically. So this is good progress, but we're not sure if string theory describes the real world, or how it's related to the real world, or what role it plays in our description of nature. And because the strings are so small, we might have a very large time, have to wait a very long time to answer that question. Meanwhile, we've got black holes. We're looking at them, we're measuring them. Why do we have to understand what a string is, all the details of a string, in order to understand the mysteries of these ginormous black holes out in the heavens? And now, when we first did the calculation, it seemed to depend in great detail on all the nuances of string theory. But as often happens in science, you peel off layers and you find the essence of something. And the essence is much simpler than what we started out with. And the essence of it is a symmetry called conformal symmetry. And conformal symmetry is a symmetry which has been observed in nature. It isn't everywhere. It's a symmetry which relates things of different sizes to one another. Now, in this room, on the scale of meters, if you were to look at me, I'm 6 feet. If you were to zoom in with a camera, you'd see the pimples on my face. Then you would further, you'd see molecules and then atoms. The scales are different. Things look different at different scales. Nevertheless, there are places in the physical universe where this conformal corners in which it emerges. An important one is the early universe. If we look at the very, very early universe, the theory of inflation, which has some good evidence, posits that there is scale invariance. There are other examples, like at a certain melting point of ice under the right pressure, you can get this kind of conformal symmetry. So just to explain to you what it is a little better, so here's a spiral that looks the same. It looks the same at every distance scale, no matter how long you zoom in. So this is a symmetry, a kind of scaling symmetry. Not around us in the world at time, but it does exist in regions of the universe. And indeed, one of the reasons in the universe where it exists is near the boundary, which we call the horizon, of the black holes that we studied in string theory. But fortuitously, it also exists near the boundary of black holes which are spinning very rapidly. They have a maximal amount they can spin. The horizon itself can't move around faster than the speed of light. And it turns out, weirdly, everything we learn about black holes is a surprise, and the astronomers have been discovering that, in fact, a lot of them like to spin very rapidly. And there are some black holes that they've seen that are within 1% of the speed of light. And the way the conformal symmetry works here is that as you approach the horizon of the black hole, it just keeps looking the same and the same and the same and the same. Now, you can't see this in the picture because I can't draw the curved space in this picture. But it has to do with the curvature of space. You get into a funnel where everything is just, you keep going and it's the same. Now, recently, so now I'm going to kind of go into a shift. Recently, there have been some really truly spectacular advances in the direct observation of black holes. And these observations have caused us looking at them and to think about them in new ways and to ask new questions. And so it's been a very exciting time, both for observers and theorists. The challenge to the observers is to build the things that see them, and the challenge to the theorists is to understand them and suggest what might be new. And one of the things that we have realized is that even black holes that aren't rapidly spinning have a conformal symmetry. But okay, so here we come to this famous picture, which I presume you've all seen. It was taken at the Event Horizon Telescope. So I just want to pause to comment about this picture because I love it so much. So when I was a graduate student, most people didn't believe there were black holes. By most, I mean like 60% of scientists didn't think that black holes were real, sort of following Einstein and so on. And then there was a lot of theoretical work on it, and then there became more and more circumstantial evidence. But there's the old adage that seeing is believing. And this here was the first actual picture of a black hole. We all like to see a picture. And so this whole century in which, I guess I realized when I saw this picture, I felt very happy, and I also felt a huge relief. Because what if I had spent my whole life working on something that didn't exist? And you're never really sure that something exists till you see it. And there it was, this picture of the Event Horizon Telescope. And it wasn't just sort of emotionally exciting, it was also intellectually exciting. And we started thinking about this, and these people are next door to me up there, or down there, whatever it is. So we started thinking about what was next. What did this mean? What did this tell us about the Einstein equation? And we had a prediction that this black hole is surrounded by a region which exhibits where this conformal symmetry, the spiral symmetry, emerges. And moreover, that it's quite possible that in the next generation of telescopes that we'll be able to see this. This is the paper we wrote on it. And so what's around a black hole is when you see it, you see something called, well, it hasn't been seen yet, but we are building the network of observations that we hope will see it. And here's what happens. Now, a black hole is like a hall of mirrors, because if you're looking at a black hole, the light from your face can go graze by the left side of the black hole and circle back around you, and you'll see yourself again. In fact, it can go back there, it can wind around once and then come back. So it's like a black hole is like a hall of mirrors, and you see infinitely many images, nested images, in fact, around the black hole, an infinite number of nested images of the entire universe. Now, in fact, of course, a lot of this light gets blocked by junk in the way and so on. But if there were nothing else and you could, at a perfect telescope, that is what you would see, an infinite number of nested images. And so let me explain, and that produces a phenomena which we propose to measure that that's called the photon ring. And so here is a simulation of it. Here is so here's the black hole. Here's photons that go halfway around the black hole before hitting the screen. The screen is the telescope. They can go one full orbit around the black hole, or they can go 2 full orbits around the black hole before they come. And so the image looks like this. What you find, the entire composite image looks like this. So here you have all the direct stuff, and then you have this very sharp, and the resolution isn't great enough here, but you have this nested sequence of rings that pile up. They're piled up on top of each other, so the resolution isn't great enough for you to see it with the naked eye, but it's definitely there. And moreover, what's really exciting is that we hope to measure it. So let me tease this out a little bit. So suppose here's the black hole. Let's take this to be M87 star. And here is a direct image of a person just coming straight to the telescope from you. But then the image you could have a light ray which wound around behind the black hole and then came to the telescope, and that would give an upside down image. You could have one that came in front, wound all the way around, and then came back. That would be a right side up, and there would be an infinite sequence of these images all converging at this locus here that is the photon ring. And these different images are all self-similar, and this is related. This is another example of this conformal symmetry. And so the proposal is for the next, we couldn't get on the Webb telescope, it was too late, but so in order to see something very small in the sky, these black holes are very small in the sky, and in order to see something small, you need a big telescope. And it turned out this amazing coincidence that in order to see the biggest black hole in the sky, you needed a telescope the size of the whole Earth. And so that is exactly what they did. They built a telescope the size of the whole Earth by synchronizing all the radio telescopes around the planet and making them into one big telescope. Okay, so that's really fantastic that they did that, really a landmark. So here's the letter here, EHT for the Event Horizon Telescope. But now, in order to see these photon rings, so in order to see the really weird behavior of the black hole, these circulating orbits and the conformal symmetry, we have to see this photon ring. And in order to do that, we need a telescope which is bigger than the Earth. How do you get a telescope which is bigger than the Earth? Well, you send something up into orbit, and then you coordinate your images on Earth with that, and that gives you even more resolution. And there are compelling arguments that this is actually plausible, that this can happen. Okay, so in conclusion, you never know what's going to come next. If you're trying to understand the physical world, it's really a weird and fun place. And we've been having a lot of fun so far, and I'm sure it's going to continue. Okay, thank you very much.